So in this lecture, I included emission spectrum of atomic hydrogen, then how Lyman, Balmer, Paschen, Brackett and Pfund series were established, and from that how RITZ equation and Rydberg constant came into the picture, and then how Bohr has given its postulates, and then he has established the atomic model which is known as Bohr's model. So Bohr's model of the atom, the outline, emission spectrum of atomic hydrogen, RITZ equation, Bohr's postulates, the Bohr model and extension to higher atomic number. So let us see first emission spectra of hydrogen atom. Under controlled conditions, hydrogen gas emits characteristics radiation. When hydrogen gas filled in a discharge tube at low pressure is subjected to high voltage, it emits characteristics radiation. This radiation appear magenta in color. When they are analyzed by means of a spectrograph, several isolated bright lines are observed in the spectrum, which we are calling as a emission spectrum. As the spectrum consists of a series of lines, it is called line spectrum. Like hydrogen, discharge through vapor state of any element gives line spectrum characteristics of the element. The line spectra of this type of emitted light is also called atomic spectra because it is a simple lines. Atomic spectra is the characteristics of the corresponding element like fingerprint. Photon emission. Here we can see in the picture that when energy is absorbed, it will go to the another energy level and it will emit the photon back. So relaxation from one energy level to another by emitting a photon. So we can use the formula delta E is equal to hc by lambda, where delta E is change in energy. If the wavelength is 440 nanometer, then we will get delta E is equal to 4.5 into 10 to the power minus 19 joule. Here in emission spectrum of hydrogen, we have compared both the spectrum, continuous spectrum and quantized spectrum. In continuous spectrum, we will have any delta E, means we can get any change in energy that is possible. While in quantized spectrum, only certain delta E are allowed, means the electron will go to certain energy level and will come back to the certain energy levels, so that are only allowed energy levels. So if we see here, two emission spectrums are given. The first one is of light bulb, in which we can see that it is a continuous type, where you can see the photographic plate where there is a continuous line are given. While if we see the hydrogen lamp, then we got only quantized, not continuous spectrum. 410 nanometer, 434 nanometer, 486 nanometer and 656 nanometer. So this is called a quantized line spectrum, which is emission spectrum of hydrogen. So as mentioned earlier, the formula delta E is equal to hc by lambda. Here we are getting 3 lambda, lambda 1, lambda 2 and lambda 3. Means this blue line is coming from upper energy level to the lower energy level. Same green line is also coming from the upper to lower energy level, and the red line is also coming from upper energy level to lower energy level. But you can see the difference in blue, green and red lines. They are coming from different energy levels, though they are upper energy levels, or we are also knowing as an excited state, right? So we can use the emission spectrum to determine the energy levels for the hydrogen atom. It shows that hydrogen can absorb n number of energy and coming back to the basic energy levels, or we can say a ground state. So as hydrogen spectrum appears complicated at the first glance, but the regularity in position of lines in different series has been proved. Different series of lines are named after the names of scientists who discovered them. They are known as Lyman, Balmer, Paschen, Brackett and Pfund series. The frequency of radiation of different lines in different series of hydrogen spectra is calculated by RITZ equation. The first visible spectra was presented by Balmer. That's why let us see first Balmer model. Joseph Balmer in 1885 first noticed that the frequency of visible lines in the hydrogen atom spectrum could be reproduced by the following formula: frequency proportional to 1 upon 2 square minus 1 upon n square, where you can take n as 3, 4 and 5, means all the absorbed energy is coming to the second series. The above equation predicts that as n increases, the frequencies become more closely spaced. After Balmer series, Rydberg had extended the Balmer model by finding more emission lines outside the visible region of the spectrum. So he has given another formula, that is frequency is equal to R into square bracket 1 by n1 square minus 1 by n2 square, where n1 is series term, which is maybe 1 for Lyman, 2 for Balmer, 3 for Paschen, so on. And n2 is known as line terms, which is like n1 plus 1 and n1 plus 2, n1 plus 3, so on. And Ry is known as Rydberg constant. Here as it is equation for the frequency, so it is in hertz or 1 per second. Its value is 3.29 into 10 to the power 15 hertz. This suggests that the energy levels of the hydrogen atom are proportional to 1 upon n square, which is very important. So this table shows name of series, series term, line term and region in spectrum. For easiness, we are making series term as capital M and line term as small n. Whenever you use n1, n2, m or n, you have to just mention what term or what symbol you are using. So Lyman, the m value is 1, while line term is 2, 3, 4. So and it is in the range of ultraviolet. So you can see here n1 and n1 plus 1, or n1 plus 2, n1 plus 3, so on. For Balmer, your series term is 2 and your line term is 3, 4, 5, so on, and it is in the visible region. Paschen, the series term is 3 and the line term is 4, 5, 6, so on, and it is in the infrared region. Brackett, the series term is 4 and the line term are 5, 6, 7, and they are also in infrared region. And Pfund, the series term is 5 and the line term are 6, 7, 8, and it is also in infrared region. There are three types of infrared: far IR, near IR and IR. So after this all observations, Niels Bohr uses the emission spectrum of hydrogen to develop a quantum model of hydrogen. What is the central idea? Electron circles the nucleus in only certain allowed circular orbit. We will study in detail. Bohr postulates that there is Coulombic attraction between electron and nucleus. However, classical physics is unable to explain why an hydrogen atom doesn't simply collapse. This picture is simplifying the above table, where we have seen series term and line term. So like Lyman series, from 6, 5, 4, 3, 2, 2, all energies are coming to the first energy level. And for Balmer, from again 6, 5, 4, 3, 2, they will come to the second energy level, that is 2. So that's why the series term is 2 for Balmer series. So let us describe Bohr's atomic model. Niels Bohr proposed an atomic model for hydrogen atom. It was the first attempt to describe arrangement of electrons in an atom. According to Bohr's concept, atom of hydrogen contains a nucleus having only one proton. There is one electron moving around the nucleus in a circular path known as orbit. As the nucleus and electrons have opposite charges, attraction exists between them. If the distance of electron from the nucleus increases, the radius of the orbit will increase. As a result, there will be a decrease in the nuclear attraction, and as a result, the energy of the electron will increase. If there is decrease in radius of orbit, the energy of electron will decrease. To explain hydrogen spectrum, Bohr made the following assumption. First assumption: electron moves around the nucleus only in certain permissible energy levels, where n is equal to 1, 2, 3, 4. They are known as orbits. We are also knowing as a shell. The electron has a definite energy characteristics of the orbit in which it is moving. As long as the electron remains in the orbit, it does not lose energy. The orbits or energy levels are therefore called stationary orbits. Thus, energy of electron in stationary orbit is quantized. The second assumption says the electron can jump from one energy level to another by emitting or absorbing discrete quantity of energy. Thus, the energy which is emitted or absorbed by an electron is also quantized. An electron cannot have an energy that would place it between two permissible orbits. Means in between two orbits, electron cannot be possible. The third assumption: electron can move only in those orbits in which its angular momentum is an integer multiple of h upon 2 pi. This type of orbit is called permissible orbit. Remember that. Thus, angular momentum is also quantized. Angular momentum is taken as m into v into r is equal to nh upon 2 pi. So this is the mathematical form of third postulate, which is very important, where m is mass of electron, v is velocity of electron, r is radius of orbit, n is positive integer, and h is Planck's constant. The fourth postulate is about energy of an electron. Bohr derived the following equation to calculate energy of electron moving in permissible orbit, and that is given by En, which is equal to minus 2 pi square e raised to 4 z square m divided by n square into h square ergs per electron, where En is energy of electron in nth orbit, where n can be 1, 2, 3, 4. E is charge of electron, Z is atomic number, m is mass of electron, n is positive integer. In future we will call it quantum number, that is principal quantum number, and h is Planck's constant. Now, if we calculate the energy of electron for 1 mole of atom, then En is equal to minus 2 pi square e raised to 4 z square m divided by n square into h square. In this, we will take n as a Avogadro number, which is equal to 6.022 10 to the power 23. Putting the values of pi 3.14, mass of electron, charge of electron, Planck constant in erg, Avogadro number and atomic number of hydrogen Z as a 1, and converting erg into kilocalorie, the value becomes minus 313.5 upon n square. This is your homework. You just do in your notebook by putting all this value and calculate this. So what you will get? Minus 313.5 upon n square. Why I have not given the value of n? Because n can be any. It may be 1, 2, 3, 4, 5. Means it is coming from 2 to 1, 3 to 1, 4 to 2, anywhere. So that's why n is not fixed. But it is going to give information about the permissible orbit. So this is the value of energy in kilocalorie per mole, that is minus 313.5. As a curious student, you must have a question. Why we have taken the value of energy with negative sign? So in the above equation, negative sign shows that N is equal to 1. Means electron is in the lowest energy level and which is known as ground state of hydrogen atom. When N is higher than 1, the energy state describes the excited state of hydrogen atom. So if we calculate N, L and delta E for the first line of Lyman series, then in the above equation which is given by RITZ, we see frequency is equal to 3.29 into 10 to the power 15, 1 upon m, where m is again series term and small n is line term. So m I am putting as a 1 and n we are putting as a 2. Means here the electron is coming from second orbit to first orbit, or we can say first excited state to the ground state. The 2 number is used for first excited state and 1 number is called ground state. So if we calculate, we are getting the frequency 2.47 into 10 to the power 15 hertz or second inverse. Now we can find wavelength from this, because we know that wavelength is equal to c by nu, where c is velocity of light and nu is frequency. So we know the value of velocity of light, that is 3 into 10 to the power 10, and our frequency is 2.47 10 to the power 15. So as we have used 3 into 10 to the power 10, it is in centimeter per second, right? So we will get 1215 into 10 to the power minus 8 centimeter, which is equal to 1215 angstrom. So when Lyman series is used, the frequency or wavelength is in this range. Further, we can also find the energy change. So again in this formula, we know the formula delta E is equal to hc by lambda. We know lambda, we know h and c. So by putting direct value 313.5 into 1 upon m square minus 1 upon n square, we know how we got 313.5. I have given you the homework. 313.5 1 upon 1 square minus 1 upon 2 square will give you 235.2 kilocalorie per mole. This shows that this change in energy is quantized. Similarly, if we want to find N value, L value and delta E of the second line of Lyman series, we can do easily. So let us understand one term known as quantum jumps or quantized electron transitions. There is no emission or absorption of energy when the electron is moving in permissible stationary orbit. It means the energy of electron remains constant in that stationary state according to Bohr's equation, and the value of that energy is equal to minus 313.5 upon n square, where n is whether 1, 2, 3, 4. Means if it is in first orbit, energy is fixed. If it is in second orbit, energy is fixed. Third orbit, energy is fixed. It is not going to be changed because there is no emission and no absorption. But the permissible energy levels of hydrogen are specific and have definite energy because the values of n is always positive integer 1, 2, 3, so on. You have studied it as shell, or that is known as K, L, M and so on. When electron jumps from higher permissible energy level to a lower one, definite amount of energy is emitted in the form of a packet known as quantum. So quantum word is nothing but called packet of energy. And hence when an electron jumps from one energy level to another, it is termed as quantum jump. The quantum jump of electron is from higher energy level to the lower one, emits one photon of definite frequency. As a result, certain spectral lines of definite frequencies are produced. Suppose the higher energy level of electron has quantum state n and the lower energy level has quantum state m, then En is equal to minus 313.5 upon n square kilocalorie per mole and Em is equal to minus 313.5 upon m square kilocalorie per mole. Here n is higher than m. So En minus Em is known as change in energy, that is emitted energy. So now we can understand that how the RITZ equation come into the picture. So from the above two formulas, we can write delta E is equal to minus 313.5 by n square minus 313.5 by m square. So here 313.5 can be common and we are removing the minus sign. So what we can write, 313.5 1 upon m square minus 1 upon n square. Now we know that delta E is equal to h nu. So from that we can get the RITZ equation, that is nu. So nu becomes 313.5 by h into 1 upon m square minus 1 upon n square. So if we put this value, this is your Rydberg constant which we have seen earlier. So in this equation 313.5 by h is constant. Substituting the value of h, which is equal to 6.626 10 to the power minus 27 erg into second, and then the necessary conversion gives the value of constant 3.29 into 10 to the power 15 second inverse. This value is same as the value of constant in RITZ equation, which we call Rydberg constant. Thus, like RITZ equation, the equation derived on the basis of Bohr's assumption also interprets hydrogen spectra. This fact supports the assumption made by Bohr. So now the picture is very clear. You can see here Lyman series from 7, 6, 5, 4, 3, 2 to first ground state. Balmer series, you are having 7, 6, 5, 4, 3 to second, like first excited state. In Paschen, all are coming to second excited state. In Brackett, all are coming to third excited state. And in Pfund, all are coming to the fourth excited state. So second, third, fourth, fifth, they are known as first excited state, second excited state, third excited state, so on respectively. So in above equation, when n is equal to 2, 3, 4, 5 indicates an electron in higher energy levels, it jumps to the lower energy level state M1. As a result, emission of the frequencies corresponding to Lyman series takes place. Similarly, quantum jump from the higher energy level 3, 4, 5 to the lower energy level M2 can explain the spectral line of Balmer series. Bohr predicted series of spectral lines in infrared region by transition of electron from higher energy level n is equal to 6, 7, 8 so on to the lower energy level M5. On the basis of this, Pfund series was discovered. Evaluation of Bohr's assumptions. First, Bohr's assumption can interpret the hydrogen spectrum. Second, the permissible energy levels in any atom can be calculated with minor modifications in the assumptions. Third, the energy of free electron at rest is considered to be zero. And fourth, the permissible energy of an electron in an atom has a negative sign, as we mentioned earlier. So let us revise it. Bohr model for the hydrogen atom is capable of reproducing the energy levels given by the empirical formulas of Balmer and Rydberg. Here, energy is equal to minus 2.178 into 10 to the power minus 18 joule into Z square by N square, where Z is atomic number. For hydrogen, we will take 1 and the small n is integer value. Here, you have seen this is third constant. That is multiplication of Rydberg constant into Planck's constant, that is minus 2.178 10 to the power minus 18 joule. Again, remember for the minus sign is just informing that electron is coming near to the nucleus. Finally, we can say that energy is equal to minus 2.178 10 to the power minus 18 joule into Z square by N square. When energy levels get closer together, as n will increase. At n infinite, E will be 0, which we have seen in the previous presentation. So again, in the form of energy, we can write this formula, delta E is equal to E final minus E initial Already we have seen this formula, so I am not repeating again. It is only in the form of joule. Earlier we have seen in the form of hertz, or we have checked the frequency formula. First example. The question is that at what wavelength will emission from N4 to N1 for the hydrogen atom be observed? Here you can ask in another way. The N4 means third excited state. So the question can be like this. Find the change in energy when electron is coming from third excited state to ground state. So the same question can be asked in this way. So if it's very simple, you just put the values in the formula. Here only variable is your n like n final and initial. So your final is the always smallest n1, and your initial is this one, because the sign is negative. So if you put 1 upon 1 square minus 1 upon 4 square, you will get 1 minus 1 by 16, and if you change the sign, you will get 2.04 10 to the power minus 18 joule. Remember always this photon energy will come in the power of 10 to the power minus 19 or 18, right? And if you take this formula hc by lambda, then you can get the lambda, that is 9.74 10 to the power minus 8 meter or 97.4 nanometer. This type of sums will come in your exam. Second example, what is the longest wavelength of light that will result in removal of the electron from hydrogen? See, it is not talking about excited state, it is talking about the removal of electron from hydrogen. Means your final state is infinite, which is we are knowing as a ionization energy. You are removing electron from the orbit of the atom. So here your n final will be infinite, and your definitely n1 is 1. So just putting the value, you are getting 2.178 10 to the power minus 18 joule. Means this much energy is required to remove electron from the hydrogen atom. And the wavelength is 91.3 nanometer. Now, as Bohr model is only for one electronic system, then how can we use for other elements? So for that we have to convert that element into one electronic system. So how we can do that? By removing the another electrons. Like if we talk about helium, then we need to remove one electron, so we have to create helium plus. Lithium is having 3 electrons, so we have to create lithium 2 plus. So if we take He plus or Li2 plus, then only we can use this formula, because this formula is established only for one electronic system. So this is showing the same way, like here Z is going to be changed. So for helium your Z is 2, for lithium your Z is 3, rest everything is same. So you keep remember this and put in your calculation. Let us see one example of it. So the question is, at what wavelength will emission from N4 to N1 for helium plus atom be observed? See, earlier we have seen for hydrogen, this is for helium, but where is the change? Change in Z. Means in all this type of question, we need to involve Z, because earlier hydrogen atom is there, so Z is 1, so it is fine if we not include. But now if Z is higher, then we need to include it. So only Z square will come. So the value becomes minus 8.16 10 to the power minus 18 joule, and the wavelength will be 24.3 by calculation. So here you can see that the wavelength of hydrogen is higher than wavelength of helium. Means if you see, wavelength and energy are inversely proportional. So it means that energy of hydrogen is lower, that's why its wavelength is higher. Part is, where does this go wrong? The Bohr model's successes are limited. It doesn't work for multi-electron atom. As I mentioned earlier, the electron racetrack picture is incorrect. That said, the Bohr model was a pioneering quantized picture of atomic energy levels. So it is only good for giving the definition of shell, which is we are calling now as orbit, right? So let us understand it in drawbacks of Bohr's model. First, each orbit of electron in the atom is circular. This assumption is wrong. We will understand it in detail in future. Second, the radius of the orbit of hydrogen electron has some definite value. This assumption is also wrong. Means it says that the radius cannot have definite value. And the third, the momentum of electron in the given orbit is accepted to have definite value in Bohr's model. This is also not true. It means that these three drawbacks is telling something else. So what is that? It means that Bohr's model is based on Newton's theory. Means it is for a big particles or macroscopic particles which we can see from our naked eyes. While electrons is a subatomic particle which we cannot see. So this all discussion we will study in the next topic, right? According to Bohr's model, theoretically calculated velocities of electron is 2.0 10 to the power 8 centimeter per second, and the radius of its orbit is 5.3 into 10 to the power minus 9 centimeter. Means velocity and radius are fixed. But de Broglie and Heisenberg, they have given their own concepts, right? From that concepts we will clarify that Bohr's model, in which orbit concept is very good, but the values which he has given, that is of velocity, of radius, they are totally wrong. So why it is so, that we will see in the next session. Thank you.